Hey, Mr. Yeller here, back in the wood shop with Module 17 on acids and bases. Module 17 is a continuation of Module 16, really, in talking about equilibrium, and it's just a kind of a special case of equilibrium. So let's go ahead and get into lesson number 1 and introduce you guys to acids and bases. So our focus question is obviously going to be, what is an acid and what is a base? And if we go around our house, we could find different chemicals in our house and we could test them if we had a pH probe. There is actually, you can go online and see how you can make an indicator using red cabbage. And so that'd be kind of a fun thing to do at home if you have the chance. Pick up some red cabbage at the grocery store and you can test out different things. You can go ahead and Google that and it's out there. Alright, so let's go ahead and we can use this simulator to kind of simulate some of those tests. If we were to test water, we would see that water is going to be neutral. It's got a pH of 7, which is neutral, and we haven't learned about pH yet. We'll dive into that more in lesson 3. But basically what we need to know right now, no pun intended basically, is if it's above 7, it's basic. If it's below 7, it's acidic. Okay, so water is neutral. Let's go ahead and try a drain cleaner. What do you guys think drain cleaner is going to be? So let's set this up. We got drain cleaner, and I'll bring that down there so we don't have to fill it up as full. Whoa, drain cleaner is very, very, very basic. All right, let's go ahead and grab a different one. Maybe we want to test our hand soap. Okay, hand soap seems to be important these days. So, that's basic as well. It's a pH of 10. Let's see, blood. Okay, so let's test blood. Blood. What's going to be? Blood is pretty neutral, which should make kind of make sense, right? So blood's kind of neutral, and so we could go through and test the different ones. Vomit. I wonder what vomit's going to be. So vomit. I remember if you vomit, it kind of tastes really in your mouth and kind of burns. I wonder what that one would be. So let's fill this up with vomit. Very, very low pH, so it's very acidic, okay, because that's coming right from your stomach. And anyway, you can play around with this. I'll leave a link to it somewhere in the video, maybe in a card up here above my head or something like that. All right, so let's continue on. Let's dive into what are these things. So here's our new vocabulary for the lesson. Go ahead and pause the video, write those down, keep track of them. Vocab is going to be huge in this lesson, so please write these down and keep notes on these vocab. All right, so moving on. Remember, a Lewis structure or a dot structure is a model that uses the electron dots around the symbol to indicate the outermost valence electrons of the atom. Okay, and we'll see Lewis structures later on in this lesson. Okay, so properties of acids and bases. So in general, acids taste sour, bases taste bitter. I would not recommend testing that out on yourself, but you could go back to maybe that list of household chemicals, and if some of those are edible, then maybe you could test that out, like lemon juice and stuff like that. But acids taste sour, bases are bitter. Acids are sour, bases are bitter. Okay, bases also feel very slippery because they're going to kind of be kind of soapy on your hand. Okay, acids and bases are conductors of electricity. So if you put them into a solution, they will conduct electricity. Acids turn blue, litmus paper red. So in general, if things are acidic, they're kind of assigned a red color, red. So litmus paper turns red, litmus paper turns blue if it's a base. Acids and bases can be identified by their reactions with different metals. So acids react with metals differently than some bases do, and these reactions have been tested out, of course, and very well known. For example, magnesium and zinc will react with acids to produce hydrogen gas. Okay, and geologists actually identified limestone in the earth by producing carbon dioxide when they drip hydrochloric acid on it. So geologists actually use chemistry to help identify rocks or minerals, things like that. All right, so properties, continuing properties, acids and bases. Like I said, on the pH scale, this would be below 7, this would be above 7. And all water solutions contain hydrogen ions I'll move my face real quick here. So hydrogen ions and hydroxide ions. Okay, so an acidic solution is one that contains more hydrogen ions, so there's H plus ions. So if we have more H plus ions present, it's going to be more acidic. If we have more OH ions present, then it's going to be basic. So that's the really simplified explanation of acid and a base. Acids have higher hydrogen ion or hydronium ion, as we'll see later, and bases have hydroxide. Okay, so if we take a look at water, let's say we just have a glass of water here. Those water molecules will actually interact with each other, and there is a little bit of an equilibrium going on there. Okay, and so you're going to form what's called a hydronium ion. This is basically just water, so H2O, plus an extra hydrogen ion, so that H plus ion attached to it. So a lot of times you'll actually see this just written as H plus instead of H3O plus. So this is showing the actual hydronium ion, and but it's just an extra hydrogen on the water. And where did that hydrogen come from? Well, it came from another water molecule. So here's water minus a hydrogen, and you'd be left with OH. And then since that proton left, so a hydrogen ion is just a proton, it left, and you'll be left with an OH minus. Okay, so here's just a discussion about the hydronium ion. So you can see it written out there. Hydronium ion is just H3O plus. So you can interchange the symbol H plus, which H3O plus, and so you can use either one of those. Usually if we're focusing on a situation where we really need to keep track of water molecules and things like that, then we would use the hydronium ion. Otherwise, a lot of times we just use H plus. All right, we're going to hop over to the Explore and Explain and spend a lot of time over there talking about the 3 different definitions of acids and bases. That's right. We can't just have one definition of an acid and a base. We have to have 3. And I'll see you in just a bit, in like a split second here. Ready? Go. Okay, so here we are over in the Explore and Explain. We're going to talk about the Arrhenius model first. So if we look at the definition here, it says that you pronounce it Arrhenius. I've always learned it as Arrhenius. I don't know. Anyway, so what does it say? Well, basically what it says here is that an acid is a substance that contains hydrogen, and it'll ionize to produce that hydrogen ion. Remember that H plus ion. A base is going to contain the hydroxide group, and it's going to dissociate, forming the hydroxide ion. So if we go back here and look at these 2 equations, we see that here's hydrochloric acid, which clearly has a hydrogen that can break off and form that hydrogen ion. Okay, and that's going to be an acid. And then sodium hydroxide is an OH group on there, so it's going to break off and form the hydroxide ion, so that's a base. So the Arrhenius definition is real simple. It's if you got a hydrogen to give up, you're an acid. If you got an OH group to give up, you're a base. Okay, let's practice that a little bit here. So in here we have to separate out these compounds or these formulas into whether they're an Arrhenius acid or base. Okay, and it says keep in mind not all molecules will fit in the bin. So this first one, do we have a hydrogen or a hydroxide? It doesn't look like it, so I don't think it fits anywhere. What about this one? So this one right here has those acids up front, or sorry, those hydrogens up front, so I kind of gave away the answer there. Here we go, we got sodium chloride, doesn't have either one. Here we have a hydroxide group, we already said that was a base. Oh, here's the hydrogens up front again, so that's going to be our acid. Here's our hydroxide right here, so we're going to have a base, hydrogen up front, we got an acid. You kind of see the trends here? Hydrogen up front, where does it go? Boom. Hydroxide at the end. Boom. Let's check our answer. Nailed it. All right. So give me a second here. We'll hop over to the next one and discuss that one. Okay, here we are over with the Bronsted-Lowry definition of an acid and a base. So remember Arrhenius, we said that it contains if it contains a hydrogen if it contains a hydrogen and produces a hydrogen ion, then it's an acid. If it has a hydroxide, produces a hydroxide ion, then it's a base. Okay, Bronsted-Lowry says that a model of acids and bases, which the acid is a hydrogen ion donor and the base is a hydrogen ion acceptor. So the first part, the acid is the hydrogen ion donor, is fairly similar to the Arrhenius definition, but it's this part, the hydrogen acceptor, that's a little bit different. Okay, so if we look at it just a generic acid here, we have we're going to identify it with the hydrogen in front, and then the X just represents some other kind of ion, and it's going to donate its hydrogen to this water molecule. So here's where we see that hydronium ion. Okay, and then it leaves our ion, or the X ion, on its own. Okay, if we have a situation where we have a base, so now we have the hydronium ion with that mystery ion over here. This is an anion. Okay, this could possibly give up its extra hydrogen ion and give it back to agent X over here. And so in that case, this would now act as an acid, okay, and it would donate it to X, and X would now be the acceptor, and so X would now be the Bronsted-Lowry base. So up here, water is acting as a Bronsted-Lowry base, and then down here, the hydronium ion is acting as the acid, and X is acting as the base. So it's about who is giving up the hydrogen and who is accepting the hydrogen. Okay, and then this brings up this concept called conjugates. So there's a conjugate acid and there's a conjugate base. So a conjugate acid is produced or formed when the base accepts the hydrogen ion. Okay, so a conjugate acid is now the new species that has the extra hydrogen that could possibly give it back up again, okay, and possibly donate it back. That's the conjugate acid. The conjugate base is the one that's produced when the acid gives up its hydrogen and now is deficient by one hydrogen ion and could possibly accept another one. Okay, and so now it becomes more of a base, and it's a conjugate base. Let's take a look at some examples here. So here again we have our generic equation, and we said that like the hydrogen up front here, so this could give up a hydrogen, so that's going to be our acid, and it becomes this guy right here, which becomes our conjugate base. Okay, so our acid turns into our conjugate base. Because why is this a conjugate base? Well, because if we ran it backwards, this thing could accept another hydrogen, or it could accept a hydrogen ion. And if you accept a hydrogen ion, then you're a base. So this is a conjugate base because it was formed when this acid gave up its proton, or its hydrogen. Okay, if we look at the base pair, so here's our Bronsted-Lowry base, and it forms the conjugate acid. Okay, because now this hydronium ion could give up its hydrogen, and so it has those acidic properties. Okay, so looking at that, here's an actual example. We have hydrogen fluoride. It's going to give up its hydrogen to, or hydrofluoric acid. It's going to give up its hydrogen to water, forming the hydronium ion, leaving the fluoride ion by itself. Okay, and so in this case, the HF is our acid, and the fluoride ion is our base, and then the water is acting as a base and turns into the conjugate acid. Okay, so that's kind of the basics behind conjugate acid and base pairs. So now water is kind of different. Water is called amphoteric. So if we look over here, we got amphoteric. Amphoteric describes water and other substances that can act as both an acid or a base. So it depends on the situation that they're in. They could be an acid or a base. So if we look at this first one here, this is the reaction that we just looked at, with hydrofluoric acid. Water is acting as the base, okay, and turning into a conjugate acid. But here we have ammonia, and ammonia can actually accept a hydrogen, and so it's going to accept a hydrogen and turn into the ammonium ion, and that means that water gave up a hydrogen and becomes hydroxide. Okay, and that would be the this would be now a conjugate base, making this the acid. Okay, so water is an acid here because it's giving up, it's donating its hydrogen, whereas over here it's accepting a hydrogen, so it's a base up here. So that's called amphoteric. All right, so let's put these in pairs. So we have, what's this guy? This has a hydrogen up front, so it's probably an acid, and that means this one's the base. Down here, we don't have any hydrogens, but we have hydrogens here, so my guess is that water is going to act as the acid here, and the CO3 is going to be the base in that case. That means that up here, this one was formed, it has an extra hydrogen on there, so it's going to be called a conjugate acid, whereas this one is deficient by one hydrogen, so it's down one hydrogen, so it's going to be the base. Here we've gained a hydrogen, so it's going to be the conjugate acid, and then that's going to be a conjugate base. Check our answers. Bammo, nailed it. All right. Hey, you know what? We're going to jump on over and learn the third one real quick, and then we'll sum this whole thing up and get on our way. Okay, we're over here looking at the Lewis model now. So Lewis models, as you might guess, might be related to the Lewis dot structure that we talked about at the beginning of the lesson here. So Lewis acids are talking about electron pairs. So in the last one, Bronsted-Lowry, we were talking about a proton donor, so the hydrogen donor. Now we're just talking about the electrons themselves. Okay, this one's a really popular one in organic chemistry. Or this definition is really popular to use in organic chemistry, but it's basically where acid is an electron pair acceptor and a Lewis base is an electron pair donor. So now they're back. Acceptors and donors are backwards, but we're also talking about electron pairs. And I think this is easier to see if we write out Lewis dot structures. So here is a hydrogen ion and a fluoride ion. And the fluoride ion could possibly give up its electrons to this hydrogen, right? And so if it accepts, this hydrogen is going to accept electrons, that means it's the Lewis acid, and this is the Lewis base. Okay. Down here, we have boron trifluoride, and we have ammonia, and ammonia has that extra set of that extra lone pair of electrons right here that it could share or donate to the boron. So we have a Lewis acid and a Lewis base here. So that's basically the rundown on the Lewis models. Okay, so let's jump back to our slideshow here and sum this all up. So Arrhenius model, remember that acids contain hydrogens, bases contain the hydroxide groups. Okay, so we saw our two examples where the acids form the hydrogen ion and bases form the hydroxide ion. So here are some of the shortcomings of the Arrhenius model, and this is why we need multiple models for acids, is that some solutions produce hydroxide ions in water even though they don't actually contain hydroxide. So the case here most commonly is ammonia. Okay, ammonia will actually form hydroxide ions when it goes into solution because it steals, this should say NH3 by the way, I just noticed that. Basically NH3 will take a hydrogen from water forming and leaving behind a hydroxide ion. So there are some cases where we can produce a hydroxide ion without having the hydroxide ion present to begin with. So that's a problem with the Arrhenius. Bronsted-Lowry model, real quick, is acids are hydrogen donors and bases are hydrogen acceptors. Okay, and then this is where we saw conjugate acids and bases. Okay, remember the conjugate acid is the species that's produced from the base, and so on and so forth. So remember they're kind of opposite pairs there. We saw some examples of those. So our hydrogen fluoride is giving up the hydrogen and forming the fluoride here. So you can see that the acid turns into the conjugate base and the base turns into conjugate acid. Okay, and same thing here. We talked about amphoteric, how water can act as both an acid or a base. Okay, and then monoprotic and polyprotic acids. Okay, well, we did not. I didn't show this over on the Explore and Explain, but let's talk about it real quick. It's pretty easy. If you have one hydrogen to give up, you're called monoprotic because mono means one, and this hydrogen ion is actually just a proton because a hydrogen atom has one proton and one electron, and an ion is the ion is missing its electron, so you're just left with its proton. So we oftentimes refer to hydrogen ions as protons as well. So it'd be monoprotic. Okay, but if you have more than one hydrogen to give up, then you're polyprotic. So this would be diprotic, and this would be triprotic. Okay, pretty simple, straightforward there. And here's a whole list of common acids and their conjugate bases. You can pause it and read that, but you don't have to memorize it or anything like that. Okay, Lewis acids and bases, remember the Lewis base is the electron donor and the Lewis acid is the electron acceptor. Okay, here's a table just kind of summarizing all that stuff. So pause it, you can write this down. This is a good table to copy down into your notes. And let's check our understanding. So number 1, and our solution. And number 2, and our solution. Number 3. And number 4. And number 5. All right, the most inclusive one is the Lewis model, and that's why it's pretty popular with organic chemistry. It takes into account, what we mean there by that is that it takes into account the most or the largest variety of molecules that we see out there, and pretty much like, well, every molecule has electrons, so they're either being donated or accepted and all that stuff. So it's most inclusive. Okay. All right, that concludes our lesson. That was a hefty one. Thanks for getting through it, and we'll see you around for lesson 2.